Welcome to the deep dive. We're here to cut through the noise and really get to the core of some fascinating research.
That's right.
Today, we're plunging into hydrogen. You hear about it all the time, right? It's seen as this, well, this cornerstone for the energy transition.
Absolutely. Huge potential as a clean fuel, key for, moving away from fossil fuels, hitting those Paris Agreement targets.
And it's versatile, packs a punch energy-wise, and we expect to see it used way more. Heavy industry, transport, you name it.
Mhm.
But, and it's a big but, its green credentials, they depend entirely on how you actually make the stuff.
That's the crux of it.
Yeah, because the truth is, most hydrogen made today, it's anything but sustainable. It's actually a massive CO2 emitter.
Staggering numbers, really.
Yeah.
Just gray hydrogen production pumps out something like 830 million metric tons of CO2 a year.
Wow. And that's what, like 2.5% of global CO2 emissions just from that?
Just from that. So definitely not cleaned by default.
Okay, so our mission today is clear. We need to unpack this. We'll walk you through the hydrogen colors, see which ones are actually, making a positive difference.
And the main event.
Yeah.
We're looking at a really novel hybrid approach. It's called pale blue hydrogen. We'll see how it measures up.
And we're basing this on some solid work, a big study from the International Journal of Hydrogen Energy.
Yeah.
They did a deep techno-environmental comparison.
Yeah, a really thorough life cycle analysis. It's crucial work because, as you said, the production details are everything.
Right. These colors aren't just labels, are they? They tell you the energy source, the method,
Yeah.
and that tells you the environmental cost.
Exactly. Without understanding the colors, you're kind of flying blind on hydrogen's real impact.
Okay, let's start with the baseline then. The most common one, unfortunately. Gray hydrogen. Why is it everywhere if it's so dirty?
Well, gray hydrogen, it's the incumbent. Mostly made using steam methane reforming SMR, usually from natural gas, about 76%.
And the rest.
Mostly coal gasification, about 23%. The big problem, as we mentioned, in the emissions, no carbon capture.
So how bad are we talking?
Around 11, maybe 13 kilos of CO2 for every single kilo of hydrogen. It's significant.
But it's cheap, and the tech's already there.
That's the pull.
Yeah.
Establish infrastructure, lower production costs. But think about the demand forecast, jumping from 70 million tons in 2019 to maybe 530 million tons by 2050.
Oh!
Yeah, relying on gray for that. It's just,
Yeah.
wow. It's unsustainable, a huge climate concern.
Okay, so that leads us to blue hydrogen, often pitched as like a bridge fuel, a step greener.
Right, blue hydrogen uses the same basic SMR process,
Okay.
but it adds carbon capture and storage, CCS. That's the key
And
difference.
then does it work? Does it cut emissions significantly?
It does make a big dent. Depending on the capture rate, you can cut the carbon footprint by, say, 70 to even 90% compared to gray. That's substantial.
But it's still using fossil fuels at the start. Right?
Exactly. That's why it's seen as transitional. It's better, much better,
Yeah.
but it's not the zero emission end goal.
Hmm.
Although, an important point from the study, if you power the SMR and CCS process itself with renewables, you can slash the overall footprint by like 94%.
Ah, okay. So
Ah.
even the energy source for the blue process matters.
Massively.
Got it. Now, the one everyone talks about, the poster child, green hydrogen.
Yes, the clean ideal. Produced using water electrolysis.
Splitting water with electricity.
Right, H2O into H2NO. The absolute key, though, is where that electricity comes from.
Needs to be renewables, wind, solar.
Precisely. Only then is it nearly emission-free. The downside, it takes a lot of energy. Over 55 kilowatt hours per kilo of hydrogen.
That sounds like a lot.
It is energy intensive, and its actual greenness. Totally tied to the grid's carbon intensity. Use the standard U.S. grid mix, for example, and your green hydrogen could actually have quite high emissions.
Right, so green depends entirely on genuinely green electricity.
100%.
Okay, so gray, blue, green, those are the big ones. But there are other shades in this hydrogen rainbow, aren't there? Just for context.
There are, yeah. You sometimes hear about turquoise hydrogen that uses methane pyrolysis.
Pyrolysis, heating without oxygen.
Exactly. It splits methane into hydrogen and solid carbon. So no direct CO2 gas released. Its impact is still there, though, sort of 4 to 6.5 kilos CO2 equivalent per kilo of H2.
CO2 equivalent. That means counting other greenhouse gases too, right? Like methane itself.
Correct. Bundling everything for a fair comparison. Then you got brown hydrogen.
Doesn't sound good.
It isn't. That's from coal gasification, and it's super carbon intensive. We're talking 18 to 25 kilos CO2 equivalent, one of the worst.
Yikes.
On the cleaner end, there's pink or red hydrogen
Hmm.
that uses nuclear power for electrolysis. Very low emissions, like zero point 0.1 to zero point 0.6 kilos CO2 equivalent.
Interesting. And yellow.
Yellow hydrogen is basically green hydrogen, specifically using solar PV electricity. So near zero emissions, assuming the panels were made sustainably, of course.
Okay, that's a lot of colors, a lot of processes. How on earth do you compare them apples to apples? You mentioned life cycle assessment, LCA. That's key here.
Absolutely critical. And that's what this study did so well. LCA doesn't just look at the smokestack, so to speak.
Right. It's the bigger picture.
Exactly. It looks at everything.
Yeah.
Energy used, transport, materials needed, all the indirect emissions too. From digging the raw materials out of the ground right up to the finished hydrogen product. That's the well-to-gate boundary they used.
And they compared everything based on producing 1 kilogram of hydrogen.
Yes, that's the functional unit. It ensures a fair, consistent comparison across all these very different methods. It gives you the real environmental picture.
All right, so we've got the landscape mapped out, gray, blue, green, and the others. But now, let's unpack this new contender. This is where it gets really interesting, you said. Pale blue hydrogen.
Yes. What's fascinating here is how this method specifically aims for a carbon-negative outcome.
Okay, wait. Carbon negative. Not just low carbon, but actually removing CO2.
That's the goal.
Mm.
Pale blue is this novel hybrid approach. It cleverly combines bits of blue hydrogen, the carbon capture part, with bits of green hydrogen, the renewable powered electrolysis.
A hybrid. Okay. Aiming for net negative. How does that actually work? Walk us through it.
Okay, so it starts with biogas, the gas from organic waste breakdown, typically about 60% methane, 40% CO2.
Right, got it.
First, a special filter, a gas membrane, separates the methane from the CO2.
Okay.
The methane then goes into a plasma reactor. Think of it as a very efficient, high-energy way to break molecules apart. It decomposes the methane into hydrogen, and crucially, solid carbon, not CO2 gas.
Solid carbon. So you capture the carbon, but as a solid material.
Exactly,
Yeah.
which you can then store or potentially even use. Meanwhile, that CO2 is separated earlier. It's not wasted.
What happens to it?
It gets fed to microalgae in a photobioreactor. Basically a system where algae use sunlight and that CO2 to grow,
Like little carbon-eating machines.
pretty much. And a useful byproduct of that process is clean water, which then,
It's used for the electrolysis part, to make more hydrogen.
you got it, so it links together. And the whole setup, the pumps, the reactor, the electrolyzer, it's all powered by solar PV.
Clever. Like a closed loop, almost. And they prefer a floating PV for this. Why float the panels?
Good question. FPV floating photovoltaics has some neat advantages. It can actually reduce the overall system cost, partly because you don't need expensive land.
Ah, makes sense.
Plus, it helps conserve water by reducing evaporation from the lake or reservoir it's floating on. And environmentally, it avoids the land use conflicts that sometimes come with big ground-based solar farms.
Okay, that's pretty smart. But putting all these bits together, membranes, plasma reactors, algae ponds, solar, it sounds complex. Does it actually scale up efficiently, or is it just a cool lab experiment?
That's always the question with new tech, isn't it?
Yeah.
And yeah, the initial experimental setup, like a lot of prototypes, had some inefficiencies, oversized components like a vacuum pump that used way more energy than expected initially.
Right. Common teething problems.
Very common. But the study modeled it out for industrial scale, optimizing the flow rates and component sizes. And the projections look quite promising.
How promising.
Well, they estimate that at scale, making 1 kilo of hydrogen would take about 165 minutes. And that key gas separation part, only using about 0.67 kilowatt hours per kilo of hydrogen. So the potential for good efficiency at scale seems to be there.
Okay. Efficiency potential looks good. So what does this all mean for the environment? Let's dive into the data. Energy use first. Cumulative energy demand, CED. How does pale blue compare?
Right, let's connect it to the bigger picture. The numbers really do show a clear hierarchy. If we use gray hydrogen's energy demand as the reference, which is pretty high, around 91 kilowatt hours per kilo.
Okay.
The most efficient, by a mile, is green hydrogen made with floating PV. It uses a tiny fraction of the energy, like 98.8% less, only about 1 kilowatt hours per kilo.
Wow, almost nothing compared to gray and pale blue.
Pale blue, specifically the 50-50 blue-green blend they analyzed, performs really well too. It needs about 82% less energy than gray, so around 16.6 kilowatt hours per kilo, second best.
That's a huge improvement over gray. What about the other blue methods?
It's interesting. Traditional blue hydrogen SMR with carbon capture can actually use slightly more energy than gray, because capturing the carbon takes energy itself, maybe about 9% more in some cases.
Huh. So adding CCS isn't free energy-wise?
Not at all. And that other blue method, the gas membrane plasma reactor one, similar to part of Pale Blue, if you power that with ground-mounted solar, it could actually end up using more energy than gray.
So the energy source is just critical across the board.
Absolutely. But the bottom line on energy is pretty clear. Lower energy demand usually means lower overall environmental impact. It's a good indicator.
Okay, that sets us up for the main event, the carbon footprint. You said Pale Blue aims for negative emissions. Did the numbers back that up?
They did, and it's quite dramatic. Again, let's use gray hydrogen as the baseline, which the study calculated at around 29 kilograms of CO2 equivalent per kilogram of hydrogen produced.
Okay, 29 kilos is our starting point.
Right now, Pale Blue hydrogen, that 50% blend, it comes in with negative emissions, minus 758 kilograms of CO2 equivalent per kilo of H2.
Minus 758. So for every kilo of hydrogen it makes, it effectively removes 758 kilos of CO2 equivalent from the atmosphere.
That's what the life cycle assessment indicates, yes. It essentially offsets or removes about 26 times the emissions footprint of gray hydrogen.
26 times. That's genuinely game-changing if it scales.
It's a remarkable finding. And interestingly, the blue hydrogen component using the gas membrane plasma reactor powered by FPV solar, that performed even better on carbon removal.
Better than Pale Blue.
In terms of pure CO2 removal, yes. It clocked in at removing over 1,500 kilograms CO2 equivalent per kilogram H2, offsetting gray hydrogen's footprint by more than 50 times.
Incredible. So these plasma-based methods using biogas seem really powerful for carbon removal.
They do. Even with ground-mounted PV, that method still offset gray emissions about 48 times over. Compare that to, say, SMR-based blue hydrogen, which reduces emissions by 70–90%.
Which is good, but not negative.
Exactly. Or green hydrogen, which also gives big reductions, 75–90% maybe, depending on the solar source, but again, not inherently negative.
So just to recap how Pale Blue gets to be carbon negative, it's by using biogas, which contains methane, and then capturing the carbon.
That's the core of it. It effectively removes methane, a potent greenhouse gas, when it uses biogas as feedstock, and it captures carbon, both as a solid from the plasma reactor and by feeding the CO2 component to the microalgae. It's taking greenhouse gases out of the system.
Very clever. Did the study look at tweaking the mix, like more blue or more green in the Pale Blue blend?
Yes, they did a sensitivity analysis, and they found that increasing the proportion of the blue component, the part using the plasma reactor, and biogas significantly boosted the CO2 savings.
Ah, so the more biogas processing, the more negative it gets.
Seems so. For instance, a 90% blue component in the blend resulted in almost 1,400 kilograms of CO2 equivalent savings, whereas a 10% blue component saved only about 150 kilograms. So that blue part is really driving the carbon negativity.
This all raises a really important question, doesn't it? How are these kinds of advancements actually shaping the global energy picture? What's the bigger context?
Yeah, good point. We're definitely seeing global momentum building for low-emission hydrogen. Countries are stepping up their commitments.
You see China, for example, moving incredibly fast. They've become a major leader in green hydrogen, now holding about half the world's electrolyzer capacity.
50%, wow.
Yeah. And the G7 nations are also making big pushes to scale up low-emission hydrogen production. There's real political will emerging.
What about closer to home? Canada, for instance.
Canada's actually a pretty big hydrogen producer already, about 3 million tons a year.
But mostly gray, I assume?
Mostly gray, yeah. SMR without CCS. But Canada has made commitments under the Paris Agreement, particularly on reducing methane emissions.
Ah, and since gray hydrogen often starts with methane.
Exactly. That commitment could definitely push the industry towards cleaner methods, maybe even exploring things like Pale Blue, which actually uses methane from biogas.
Looking ahead then, where do we see hydrogen making its mark? It's currently used mainly in refining and making ammonia, right?
That's right. But the big growth areas projected are heavy industry think, steelmaking, chemicals, and long-distance transport. Trucks, ships, maybe even planes eventually.
Sectors that are hard to decarbonize otherwise.
Precisely. In a net zero by 2050 scenario, those sectors could make up a third of all hydrogen demand by 2030. That's a huge shift from less than 0.1% today.
So studies like this one, showing these different pathways, especially potentially carbon negative ones like Pale Blue, they're really crucial for figuring out how to meet that demand sustainably.
Absolutely. They light the path forward, showing it's not just if we use hydrogen, but how we make it that truly matters. And Pale Blue stands out as a really novel, potentially very impactful option.
So let's wrap this up. The big takeaway seems clear. Hydrogen is a vital piece of the energy transition puzzle. It offers huge potential.
Hmm.
And it's the theme of our whole conversation, its real impact hangs entirely on the production method. Is it clean, or is it just shifting the emissions problem?
And what this deep dive shows us is that innovation is happening. New methods like pale blue hydrogen offer genuinely exciting possibilities, maybe even a way to produce fuel while cleaning the atmosphere.
A carbon-negative pathway. It's a powerful idea. It shows that technology really can help tackle these massive environmental challenges we face.
Definitely gives you some hope.
So here's something for you, our listeners, to think about. We've seen this spectrum, right? From dirty gray hydrogen all the way to potentially carbon-negative pale blue, with huge differences in energy use and emissions in between.
Massive differences.
Knowing this, how might you evaluate these different hydrogen pathways? If you were prioritizing investment or policy, how would you weigh these factors to genuinely speed up global decarbonization?
Yeah, what's the smartest way forward? It's not a simple question.
It really isn't. Something to mull over. Thanks for joining us on The Deep Dive.